Okay, today we're going to talk some more about energy storage and energy storage in supercapacitors. It's going to be a little bit different from what we've been talking about and a number of other people have talked about on YouTube in terms of their supercapacitor construction and recipes. We're going to go off on a little tangent. Instead of talking about electric double layer capacitors, where we're looking for a couple of porous electrodes with a separator and electrolyte in between, we're going to take a look at another part of the capacitor equation and talk about trying to achieve large amounts of energy storage by maximizing the dielectric component. If we look at a classic equation for a capacitor, the capacitance is equal to some dielectric constant times the area of the plates of the capacitor divided by the distance between the plates. So let's say we have a positive plate, maybe a cathode side, and a negative plate or an anode side, and in between the two plates we have a dielectric, and that dielectric has a certain dielectric constant. We'll talk about that a little more in a second. Well, we can maximize the area of the plates of the capacitor, and in a certain sense that's what we're doing when we build up a supercapacitor with, let's say, a very porous activated carbon. The activated carbons with all of the microscopic pores, which can be, let's say, 1 to as much as 3,000 meters per gram of material, gives you a very large area and therefore a very large capacitance for a given dielectric and distance between the plates. Really not appropriate, I guess, to talk about dielectric constants and distance when we talk about a double layer capacitor, because what we're really talking about there are little nooks and crannies for ions to park, and we're really looking at a capacitor there which has a separator in between that allows ions to pass from one side of the capacitor and collect in the pores of the other side, preventing any electron flow which is external to the circuit. In the classic sense, this capacitor equation mainly is describing an electrostatic capacitor. So here we have an electric double layer capacitor, and here we have the classic electrostatic. But in any sense, what we're trying to do here is to maximize the energy storage, where energy equals 1/2 C capacitance times the voltage across the capacitance squared. So maximizing C or raising V is obviously going to store more energy. In the capacitance equation, maximizing area, minimizing D, or increasing dielectric constant is going to give us more capacitance. So that is a little bit of a background. What options do we have, and why is this thought process here been a little bit in the background lately? Well, going back to fairly recent history, in about 2014, a number of people, researchers, started looking at trying to raise that dielectric constant, where in the typical ceramic or mica type capacitors, the dielectric constant values are relatively small. Matter of fact, the best dielectrics in those capacitors the dielectric constant approaches 10 to the fifth, and most of them much less than that, and that yields capacitance values in the picofarad to let's say hundreds of microfarad range. Microfarad would be 10 to the minus sixth farads, and for the energy storage we're looking at not microfarads but actually farads. So we need to increase these dielectric constants by about a factor of 1,000,000. And in fact, that's what has been done. Today, there are dielectric constants that people are experimenting with and have shown to be as much as 10 to the 11th. So a million times more than the best traditional dielectric constant, which allows us to get up into this farad range and reasonable values for energy storage. When we talk about double layer capacitors, there are numbers approaching 2 to 300, I believe, joules, watt seconds, per centimeter cubed. So that's a volume. This is an amount of energy, so they can reach that. Well, it's also been shown fairly recently that getting to the 200 and not very far away from 300 joules per centimeter cube is what's possible with super dielectric capacitors. Now, what really constitutes a super dielectric, and how do you get there? How do you experiment with it? How do you measure it, etc.? Well, going to one of the papers published a couple years ago, and there's a number of them, and I'll put some references up on the screen and list a number of papers and some of the more recent patents that are out there. A lot of the work has been done by a Professor Jonathan Phillips. Dr. Phillips resides at the Naval Postgraduate School in California, and him and his students have published a number of papers talking about super dielectrics as a mean to increase capacitance for energy storage. And when we talk about how we store energy or get more energy in these dielectrics, quoting from one of his papers, we talk about increasing the number of dipoles between two charged plates. Okay, so we want to fill this with a dielectric that has a number of quote dipoles between the charge between the voltage that we're putting on this plate and this plate, creating electric charge between them. And from one of the papers at the Naval Postgraduate School, I'm going to quote here: any non-porous solid in which pores are filled with a liquid with a sufficient concentration of dissolved ions will have a high dielectric constant. The concept underlying this concentration of dissolved ions is such that they will migrate to form giant dipoles in the presence of an applied field. These dipoles will partially cancel the field created by the species on the electrode plates, therefore allowing more charge to collect on the plate for any given voltage, more than is possible with another type of dielectric. So if this dielectric contains these little dipoles in here, it's going to build up kind of an internal charge, allowing the charges to migrate or collect on these plates, and that's basically what we want to do to create this capacitor effect where we have charges here and then electrons flowing in an external circuit. Okay, so much for the theory. Again, I'll let everybody visit and read a number of these papers and patents, and if you want to delve into that a little more, you're more than welcome to. But let's talk about some of the experiments I've done. When they talk about these dipoles, we have to come up with an ionic concentration, and you can start with anything from sodium chloride to KOH to some of the other salts that we've used as electrolytes in some of our carbon double layer capacitors. I should mention that our well-renowned YouTube chemist Robert Murray Smith, about little over a year ago, put out a very interesting video. I believe he called it the strange capacitor. I guess that's appropriately named because here, up to this point, we're talking about carbon electrodes and a separator in between, and we're getting these large ion flows. But here in the superdielectric capacitors, not unlike any other electrostatic capacitor, there is no separator, there is no membrane. It's just a dielectric between the plates. But yet we're getting these dielectric constants 1,000,000 times larger than is typical in the best commercial electrostatic capacitors. So yeah, I guess that's a strange phenomenon. Well, to multiply the number of dipoles, increase the dielectric constant, it seems like what you want to do is to provide little parking spaces, little pores, call them ionic condos, if you will. And a lot of the research started out talking about little tubular structures created on these plates as parking spaces, if you will, for the diodes, or the dipoles, sorry. And when you fill them with the ionic liquid, they will build up the charge on the nanotube surfaces. Other approaches, and again I refer back to the work that Robert did where he shows this quite well in his video, we're talking about creating a liquid or a gel in here that kind of suspends the ion transport liquid, and that gel then will create these little voids or pores, again, for these dipoles to build up. Other papers have talked about creating pores. Matter of fact, one of them was rather interesting. They took the traditional, let's say, carbon capacitor, where you've got maybe a graphite current collector on one side, a graphite current collector on the other side, and there is no active, let's say, carbon collector material, but they took the separator that might have been used in the double layer capacitor, and they created very small pores in this separator, okay, as parking spaces or sites for these dipoles. And that's where I started. That's where I started to think about this. So how do we create these spaces that we're going to fill with this ionic liquid, this high salt concentration liquid, and see if we're going to get some, fairly large, decent capacitances. For my previous work in this area, where we're trying to make relatively small improvements with better carbons, better electrolytes, additives, increasing pores, number of pores, controlling pore size. We're usually making fairly small improvements from each test to subsequent test. And if the improvements are relatively small, we don't want the test setup to have a variable in the method. So I've kind of adopted a standard little test fixture here, this little two-part hockey puck. We've got a graphite current collector on this side, a graphite current collector on this side. Both of them are backed with a little copper plate that I've soldered the input and the output wires to. I can put this sandwich together. I know it's always the same size. I know the pressure. when I put it together in some type of a clamp is going to be constant. So I'm controlling the pressure and the size and let's say the gap, and trying to eliminate as many variables as possible in my testing. So if I do make a relatively small improvement, it's not going to be masked by other uncontrolled variables in the test fixture. So we've done that. Well, I started out trying to create these little sites, if you will, by taking a piece of paper. And here you can see a paper that I've run through my laser cutter, and basically laser cut the array of holes here. So each of these little holes in this piece of paper, I'm going to do a couple different things when I cut out a little circle to put in the test fixture here. First of all, I'm going to control the distance between the two plates, because that's a function now of the thickness of this paper. That's relatively thin. And I've got all of these little sites, if you will, that hopefully will be little pockets to hold this fluid in place and create dipoles. Now I imagine the dipoles down at the atomic or electron layer are very small, but the papers, again, somewhat to my confusion, talk about super dipoles or dipole groups or whatever. So these little sites, I call them dipole condos, are set up to kind of control the structure of that electronic array, if you will. So anyway, we tried this paper, and that didn't work too bad, other than the fact that it's paper and it kind of quickly dissolves from the electrolytes we're using. For all of the testing that I've done, since it's kind of an outgrowth of things that I've done with the double layer capacitors, I'm now using a zinc sulfate solution. So far it's been a 1 molar zinc sulfate solution. What that allows me to do is to, at least in the double layer capacitors, get a little bit above the dissociation threshold for water, around 1.2, 1.23 volts, and I can charge to a little bit of a higher voltage and obviously get a little more energy out. But anyway, we graduated from these relatively large holes in this paper to let's see, we went and took and kind of made a miniature version of that. I don't know if you can see this, if it's going to focus very well, but this is a little piece of polypropylene, and I don't remember the exact dimensions, but you can see that there's a very fine array of holes that have been laser cut in this material, and I can put multiple layers of this together and build up a sandwich with a whole lot of sites, if you will, for the dipoles. So we would take this material, put our anode and cathode current collectors on either side, and I would just literally dip this into the electrolyte, shake or wipe off any excess. One of the things, if you watch the RMS video or you read these papers, you will hear or see the term over and over: incipient wetness. Incipient wetness. So the electrolytes you're putting in here, in these pores, should be at the level of incipient wetness. Now what does that mean? Well, kind of like Goldilocks. Not too dry, not too wet. If it's too dry, there's no ionic dipoles created. If it's too wet, I don't know if they're created or not, but they're too dispersed and insignificant in terms of holding a charge. So you want something that's wet but not too wet. And I wish I could define that better, and I think that's a lot of the experimentation we'll be doing in the future to try to control that and see where that goes. Well, from here, if what we're trying to do is to create as many of these sites as possible in a controlled fashion, maybe we want to go to a thinner material. So basically the next step was to take this thinner cellophane type material, put similar hole patterns. This is about as small as I can get them on my laser cutter. So it created these little filters, if you will, out of this cellophane with thousands of holes and creating a lot of sites. And I'll share some of that data with you, but I want to kind of get to where the latest tests have gone. From there, it was rather time-consuming to make these hole-type filters devices. In my particular laser, I did not go to a pulsed arrangement. This was basically scanned, so back and forth, back and forth. It probably took about, I don't know, maybe 5-10 minutes to make one of these patterns because of the relatively slow, precise scanning that you're doing to create the hole patterns. But from there, I noticed that the smaller the holes and maybe increasing the number of layers, in other words, stacking up holes, improve the performance. Well, what we ended up with after a few dozen more tests was migrating to a fabric. This is a very, very, very fine fabric. I'm sure you can't see it, the weave on the video here. And I don't really have a way to microscopically show it, but think of it as a very sheer material with a very, very fine weave. It's actually a delicate material that my wife uses, and when she's making like certain wedding dresses, wedding garments, okay? It's very delicate, very fine, and if you could see the pattern, the weave, the pitch, it's probably 10 times finer than what I was able to do on the laser cutter here. So we take one of these, put it in here. It's not really a separator, remember, it's full of holes, but it's insulating. It's enough thickness that it is creating a gap, insulating the current collectors, and it has thousands of sites to create our dipoles. And in fact, what I ended up doing, the last test, and again we'll report out some of that data, we had 6 layers of this put in there, and each of these were soaked, again at that, quote, incipient wetness level, stacked together and put in here. As it turns out, one of the papers that was published in the last year or two, I believe, did exactly that. They talked about using fabrics as sites, if you will, or I guess I would call it kind of a lattice. You want to create a lattice for these dipoles. Now, maybe the end game, not unlike RMS showed, the lattice can occur actually in a gel or a paste type structure, but or a combination. But in the meantime, I was able to get some very good results by just taking this cloth, briefly soaking and removing most of the moisture from it from the zinc sulfate solution. So I'm going to stop here and then come back with some of the data that maybe here's what the cloth looks like when you buy it. It just doesn't like any other cloth, comes in a roll, but it's very sheer. But we'll be back and share some of the data with you, and actually it's looking pretty good with a lot of things, a long list, I guess, if you will, for possible improvements.